try to go forward. Okay. So let's get there first. Okay, so to review very quickly, last class we saw that atoms have discrete levels. When we bring the atoms together to form crystals, they form energy bands, which can have complex shape with band gaps and so on. Okay, so far that's what we know. We went through metals and what's the difference between metals, semiconductors, and insulators, and we'll just summarize that quickly. Okay, which is basically shown here. We saw this last class, but let's just review it. So, as we saw in semiconductors and insulators, we have two separate bands, okay, which are separated in energy by what's called the energy band gap, this EG. Okay, so there's a completely filled valence band, there's a completely empty conduction band, and they're separated by the band gap. The difference between so from a qualitative perspective, the semiconductor and the insulator are the same. The difference is the fact that the band gap of a semiconductor is much smaller than that of an insulator. Okay, so that's the main difference. For a metal, the bands look very different, and this has to do. It can look in two different ways, as shown here. You can essentially have a partially filled conduction band, which means there are electrons in there. Of course, if it's partially filled, there are also available energy states, which means the electrons can move into those states. So it's a good conductor. You can also have an overlap of the bands, so no band gap at all. The result is the same, right? You have electrons at the high states, and very close by in energy, you have available states that these electrons can move into. Okay? So that's the main picture I want you to keep in mind as we go forward. Because we're going to, the energy bands tend to be quite important to calculating currents and so on. Of course, the transistor passes a current, so we need to understand how currents behave in semiconductors. So we need to understand the shapes of bands and so on, and we'll go into that today. Okay, so of course we know that by imparting optical or thermal energy, the electrons here can be excited here, and then it becomes a conductor. Okay, so we'll see this again. Okay, this is where we stopped last time. We were going to discuss direct and indirect semiconductors. So there are two kinds of semiconductors from the energy band diagram, direct and indirect. And we saw this briefly on last Tuesday. Basically, direct semiconductors mean your minima of the valence band and the maxima of the valence band and the minima of the conduction band coincide in momentum. We'll see that today. Okay. So in order to quantitatively analyze the energy bands or the energy of an electron, we need to make some assumptions for the wave function of the electron, and we need to solve the Schrodinger's equation in a crystal. It turns out to be a complicated problem, so we won't actually do it, but we need to understand some of the assumptions involved, okay? Because that is important for defining some of the terminology that is going to come up. First, we will assume that an electron traveling through a periodic crystal lattice is described by its wave function, which is what we saw last time. But now, except that we have a wave function which is sitting in a periodic lattice. Okay, so you have a periodic array of atoms, so you have periodic potentials. Okay, the wave function is typically assumed to be a plane wave. That's reasonable. Of course, a plane wave is, as we saw on Thursday, is not a realistic thing because it extends to infinity. Right? Its energy is infinite and so on. So it's not real. But mathematically, we can define the electron as a plane wave because it's simple. It's a simple thing to analyze. And that's what it looks like. So you have a wave function which has a space coordinate. So it's time independent. We're just looking at one snapshot of time or a steady state. Okay? You drop the time component. You have a momentum component, you have a space component. So you have an amplitude, which of course depends on the lattice. So you have to solve the Schrodinger's equation to see what that amplitude is. So it depends on the lattice primarily. And then you have the wave part. That's just the plane wave, which we saw last class, by the way, in one of the examples. Straightforward. So the amplitude is modulated by the lattice. So based on the spacing of the lattice or potentials in the lattice, that changes. In any case, we are not going to solve it because it's too complicated, but I want you to keep this picture in mind. Imagine a plane wave passing through a crystal in an array of atoms in 3 dimensions. Okay, that's what an electron looks like. A free electron looks like. Okay? A bound electron, of course, doesn't go anywhere, so it's not a plane wave. So one important consequence of this assumption is that we know that the lattice is different in different directions. Remember, last Tuesday we talked about the different crystal lattices, and as you saw, especially in silicon, as you rotate them, they look different. 100 is different from 111, and so on and so forth, which means that the potential that the electron wave will see will be different in different directions. Okay, that's common sense. That's what we would expect, which means that this part, excuse me, of the wave function will be different in different directions. As a consequence, of course, this part also determines the energy of the electron, if you think about it. Okay, well, we'll come back to that later. Which also means the energy of the electron also depends on which direction the electron is going, which is a little bit of a, excuse me, a strange concept. Okay, so it's not just the kinetic energy. Of course, the kinetic energy doesn't depend on direction. There's the potential energy. Okay, which depends on direction because the crystal lattice looks very different in different directions. So it's a little bit intuitive if you think about it. Okay, so keep that in mind. Which means this picture is incomplete. Okay, here we don't have direction. We only have energy, right? We only have a vertical axis. The horizontal axis is meaningless. So this is what's referred to as a simplified band diagram. In a real crystal, band diagrams don't look like this. They have a horizontal axis as well, as we will see next. Okay? So keep that in mind. But we'll come back to the simplified band diagrams because those are much easier to draw and easier to understand. Okay. Keep that picture in mind. The band structure looks like this, and it's 3-dimensional. Okay? So let's focus on the left-hand side for now. So the vertical axis is energy. Energy increases going up. So for now, we're talking about energy of an electron. Okay? The horizontal axis is direction. Okay? But it's written in terms of k, which is the wave vector of the plane wave that we assume the electron to be. Okay? If you recall, in our example last week, we proved that k is equal to the momentum. Remember? We proved this. One of the examples. So this is just a constant, right? So this is proportional to the momentum of the electron. So what we are plotting here is essentially energy as a function of momentum. Of course, momentum has direction. Remember, momentum has 3 components: px, py, pz, which means that energy has direction. Of course, so these plots have to be in 3-dimensional space. So this is also an approximation, okay, because we are not showing that. So keep that in mind, and we'll come back to that again later. Okay, the next few things to concentrate on. So we see 2 bands, so that's the valence band. So instead of having a straight line, now we have something like a parabola. Okay, and that's the conduction band. Okay, again, instead of having a straight line, we have something like a parabola. It essentially means that as the electron momentum increases from 0, your energy increases faster, which faster than linear, which of course kind of makes sense because remember that also includes kinetic energy. As momentum increases, kinetic energy has to increase. Okay, so recall, what is kinetic energy? Half m. Classical kinetic energy is just that, right? Half mass times velocity squared. We can also write this as half m. Right? Which is nothing but Okay? Mass times velocity is momentum. So from a classical perspective, all of this still makes sense. Okay? Sorry, what I meant to say is that from a classical perspective, kinetic energy is directly proportional to momentum. Actually, this is... Actually do this properly. My mistake. Okay? Is that clear? I'll just walk you through it. Kinetic energy is half m squared. You can write that as half p squared over m. So you can see kinetic energy is proportional to square of the momentum. So from a classical perspective, if I draw this, of course I'll get a parabola, right? So it's not that surprising what we see in the band. Because this is total energy, it's kinetic plus potential. Of course, potential energy will also come into play, so it's not really a parabola. There are other terms involved there, which we won't worry about too much, because this is not a math class or a physics class. Okay? Okay, the few other things to keep in mind, and we'll come back to that, so don't worry too much, is that this is the band gap. So remember, now the band gap is defined as the difference in energy between the lowest energy level of the conduction band and the highest energy level of the valence band. Because they have shapes, you can have different values, right? They're not constant. So keep that in mind. So that's the band gap, Eg. Okay? So that's gallium arsenide. So one important property you can see for gallium arsenide is that the highest point of the valence band and the lowest point of the conduction band have the same momentum, same K. In this case, K equals 0. Okay, they're aligned to each other. The two parabolae basically aligned to each other. Not always the case, as you can see for silicon. Okay, and such a semiconductor is called a direct semiconductor. Okay, and it has very important technical implications. This is the reason, actually we'll come to that later, but keep this in mind. If you have an electron, which is here, and it gets excited up here by, let's say, thermally or by light or heat, whatever, if it relaxes back to the valence band, it can release a photon of energy Eg. Okay, we saw that last time. But here, we have a big advantage in this transition because there is no change in momentum. Okay? This turns out to be technologically very important. I'll reiterate that in a second. Now let's look at silicon. Silicon, again, the same thing. You have vertical axis is energy, horizontal axis is momentum. Okay? You see that now, again, you have a band gap. But now you see the valence band is, the conduction band is shifted with respect to the valence band. Okay? So, now what's the band gap? Of course, the band gap is still defined as the highest point of the valence band, which is here, and the lowest point of the conduction band, which is there. And the vertical distance between them, right? That's the energy difference. That's still the band gap. But now, if an electron is up here and needs to relax down to the valence band, it needs to undergo a change in momentum, as shown here. Okay? So an electron in silicon, if it's in the excited conduction band, in order for it to relax to the valence band, it needs to lose momentum. And typically, the way it happens is by colliding with vibrations in the crystal. So the crystal itself is vibrating because of thermal energy. It's not sitting still. So there are what are called phonons, which we will see later on. So the electron exchanges some energy and momentum. So you see here, the electron's losing some energy, right? That's energy. So it lost a little bit of energy and also momentum. Okay? And it comes to some sort of a state like that, which can happen in a variety of ways, which we will see later on. But for instance, it could be a defect. It could be a defect in the crystal. It's not a perfect crystal. You have some defects, and they can form some extra energy levels within the band gap. Okay? Don't worry too much about it right now. We'll come back to that. And then it can emit a photon. Okay? So you can see clearly one obvious difference between the two. the energy of the photon that this can emit is higher than the energy of the photon this can emit. Right? This gap is smaller because it has to lose a little bit of energy to change in momentum. Okay? Now this is silicon. The big technological impact of this is that it's very, very difficult to form light-emitting devices with silicon. So you do not see today LEDs made out of silicon. And this is the basic reason for that. LEDs are primarily, and lasers for that, primarily made out of direct bandgap semiconductors, like gallium arsenide, gallium aluminum arsenide. There are many others, but not silicon, although silicon is the cheapest material to use if you could. Although nowadays there's a big effort at many companies, including Intel, IBM, and so on, to make lasers in silicon. And that involves a completely different process. We won't really talk about it. But this is it has very important technological implications. Okay? Recall that gallium arsenide is 3 or 4 orders of magnitude more expensive than silicon. So think about it. If one could use silicon, you would use it. It's a lot more expensive to use that, but you cannot. And this is the fundamental reason. Okay? Okay, we talked about that. So this was from last example. Okay, so that's the difference between direct and indirect bandgap semiconductors. And this is basically summarizing what I just said. In a direct bandgap semiconductor, there's no momentum change involved, so the electron can relax straight down and emit a photon. Whereas in an indirect bandgap semiconductor, some energy has to be lost as heat in the crystal lattice because of the change in momentum involved. Okay, so keep that in mind as well.
With indirect,
yes.
Does that mean it takes more energy to excite an electron than just...
Same thing, yes. It's the same principle. Because again, to excite it, which means you need to change the momentum as well, which means it needs to go to a transition state. Okay? At the end of the day, these turn out to be probabilities. So there's a lower probability that you can excite an electron this way. And for silicon, there tends to be some advantages because sometimes you do not want thermally excited electrons to reach the conduction band, because they will. For instance, a simple example is if you have a transistor made of silicon, if thermally excited electrons get into the conduction band, they can open a switch, close a switch. Let's say a switch is open, and if you just have some heat, ambient heat, electrons get in there, it can close the switch. And that's a problem, right? That will be noise in your transistor. We'll see this later on. Okay, so that was actually the end of that. So let me go to today's lecture. So that I have to... So in the next part of the class, we will talk primarily about how to do calculations based on these. Okay? Let's see. Where is it? Okay, so how will we quantitatively analyze energy bands? Okay? And for this, we have to make some assumptions. But like I said, we have to solve Schrodinger's equation in a crystal lattice, which is a very difficult proposition. So we need to make some assumptions. Okay? So we're interested in understanding how the charge carriers in semiconductors behave and what they are and so on. Okay? That's the goal. So before we jump into that, there's one other topic from the last subject on energy bands we should understand qualitatively. This has to do with varying the energy bands by alloy composition. What that means essentially is that we can so nature gives us certain materials like silicon, gallium arsenide, whatever, and the energy bands are fixed. So you can't really do anything. If you want to engineer energy bands, you can do that by adding some different kinds of elements. So gallium, aluminum arsenide, so man-made materials. And this can be done, for instance, it's hard to see. So this is gallium arsenide, okay, what we saw before. But now we have also added a couple of other bands on the sides, okay. So we have a couple of terminology I need to point out. First is that this point here of the crystal direction, when k equals 0, in gallium arsenide is referred to as capital gamma. It's hard to see for you guys, but that's what that is. Okay. The next higher valence band is referred to, whose K vector right here is referred to as F. Again, you don't need to memorize any of this. You can look at this up. But again, just a convention. And the next higher band is referred to as X. So recall that this is different momenta. Okay? So this is a direct band, and of course you have other bands as well. Okay? What happens is that, so that's the lowest band gap for gallium arsenide is about 1.43 eV. The lowest indirect band gap is about 0.3 eV more, electron volts more. Okay? The next lowest band gap is shown there, and so on and so forth. The key things to remember is that at room temperature, there are very, very few electrons here. Why? Because they're higher up. So there's no thermally excited electrons, much lower probability. Okay? Now, if you replace the gallium with aluminum, as shown here, so what we did, gallium arsenide, replace this with aluminum, the gallium with aluminum, then you get a completely different band gap. And that's what's meant by engineering the band gap. So you can change the elements to get different band structures, okay, within some limitations. So clearly what has happened now is that the band at gamma has gone up, whereas the band at X has come down, and band at L has come down a little bit. So is this, what kind of semiconductor is this? Is this direct or indirect? Right. Because the lowest band gap now is out here, right? Which is a different momentum. So what this suggests is that by changing the elements, you can not only change the shape of the band structure, but you can also convert it from direct to indirect. You usually want to go the other way, right? You don't want, if you are trying to make light emitting devices. Okay? Okay. So that's what's shown in this graph. You can do something in between. You partially replace some of the gallium with aluminum, and you form what's called gallium-aluminum arsenide, and then you have different fractions of aluminum and gallium. Okay? So you can go from 100% gallium to 100% aluminum, which is the two extremes that we just saw. But if you do something in between, and you plot the band gap energy at the three crystal directions as a function of the fraction of aluminum, you see something like this. So let's look at X, which is the K equals 0 band. For gallium arsenide, the band gap is somewhere there. That's X equals 0. That's aluminum fraction is 0. That means it's completely gallium arsenide. And X means it's a direct band gap. It's when K equals 0. Two bands are aligned. As you increase the aluminum fraction, this increases slightly, but you can see these two starts increasing as well. Okay, at some point they cross over, and then this becomes an indirect band gap material. Now, of course, for light emitting devices, you want to keep them direct, but you still want to be able to adjust the bands, which means you have to stick within this region. And you can change the energy a little bit, which means you can change the color of the light that's coming out. Infrared to red, very small amount. So that's an example of how people make different color LEDs, for instance, light emitting diodes or lasers. Okay? So that's a way, again, to do band gap engineering, to change the structure of the crystal. We'll come back to this later on, excuse me, when we talk about these kinds of devices. Okay. Okay. So you can see below that line is direct band gap, above this line is the indirect band gap, as I mentioned. Okay, so that's again just qualitative understanding of band gap engineering. Now we're going to jump into charge carriers and semiconductors. So how do we model them? How do they behave? And so on and so forth. Okay. First, let's look at metals, because they're the easiest to understand. Okay, metals, current conduction in metals is based on a very old model, over 200 years old, called the Drude model. Okay. Because the idea is very straightforward. If you have the metal ions are surrounded by a cloud of free electrons, as we saw, because remember, you have a cloud of delocalized electrons which are shared by all the ions, When a voltage is applied, the electrons are free to move. Okay, very simple. And without going into any of the math, there's a very simple video which shows this. So you can see that's a metal, a whole bunch of ions here, a whole bunch of delocalized electrons. Okay, the black dots are the electrons. As you apply so it's when the switch is off, as shown here, the electrons are just floating around with just thermal energy. Nothing happens, yeah, randomly moving around. As soon as you turn on the switch, you will see an electric field is applied. The electrons move opposite to the electric field, as we know. Okay, so you see, and the electrons will just, because they're all delocalized, they're free to move across, following the electric field. Okay, very simple idea. And of course, we can model this and so on. We'll model this more quantitatively later on. Okay, so this is the picture of conduction in metals. Okay, the conduction in semiconductors is very, very different. So I want you to contrast that to this. Okay. So the first idea to remember is to again to review the band structure of semiconductors compared to metals. So in semiconductors, we have a completely filled valence band, completely empty conduction band. If that's what we have, there is no conduction, right? Because the electrons here don't have any energy states to move into without extra energy. And up here, you have plenty of states, but there are no electrons to move. So basically, they're all held. Remember the other picture where all the electrons are essentially held in covalent bonds. They're just held together. Nothing happens to them. They're not like freely floating around, okay? Compared to the metals, as we saw before. But, as we saw earlier, at temperatures greater than 0 Kelvin, some of the electrons can gain some thermal energy and get excited from the valence band to the conduction band. Okay? Then what happens? Then you have a situation which looks like this. Okay? You have electrons up here, and you have some empty states up here where the electrons used to be. So if you think about it, of course, these electrons are free to move because there's plenty of energy levels here. There's a few electrons and lots of energy levels. Okay? So if an electric field is applied, these electrons can move very easily. Okay? Here, the opposite happens. There are lots of electrons and few energy levels. But those few energy levels are enough for the electrons, some of these electrons to move into. Okay? These, of course, are electrons excited into the otherwise empty conduction band. And these are referred to as holes, which is an absence of electron. Okay? Empty energy levels in an otherwise filled valence band. And we need to account for both of these to really explain currents in semiconductors. So that's the next new concept I want you to understand. Electrons and absence of electrons, or holes. So very different from metals. Okay? You have to account for both of these carriers, charge carriers. Okay, we'll look at this more closely soon. Of course, if you have a pure semiconductor, which is also called an intrinsic semiconductor like silicon, there are no impurities, then for every electron that's excited from the valence band into the conduction band, there is a hole in the valence band because it left behind an energy level, right? So electrons and holes are always in pairs. So they're referred to as electron-hole pairs, or EHPs. Okay? So that's the basic difference between metals and semiconductors. So for reference, at room temperature, silicon is about 10 raised to 10 electron-hole pairs per centimeter cube density. That's a small number compared to the density of the atoms themselves, which is about 10 raised to 22, 5 times 10 raised to 22. So very, very few electrons available, which is why silicon in general is a poor conductor, even at room temperature. You need to do something extra to make them better conductors, like doping, which we will see. Okay? Okay, now how do we analyze charge? So first of all, the charge transport with electrons in the conduction band is exactly the same as metals, right? So if you go back and think about this for a second, this looks just like a metal, right? A metal is an incompletely filled conduction band, which is what this is. So there's nothing special here. It's very easy to model, just like a metal. Okay? But the hole is much more complicated. So we need to have some special treatment to really understand this. Okay? So charge transport by a hole. So you have conduction band, you have valence band, as we saw before. So in this situation, there are no electrons in the conduction band, no holes in the valence band. If you want to calculate current, what would you do? You would look at every electron in the crystal, look at its velocity, add them up with the vector, right? Velocity is a vector, which is what's done here. So you take the velocity of the electron, multiplied by the charge of the electron, add everything up. That'll give you the the current. Remember, current is nothing but moving electron, right? Charge transfer. In principle, this is current density, because N is typically in per unit volume. Now, this is 0 primarily because if you look at the band diagram of the valence band, which is K, remember K is proportional to velocity. If I pick a certain energy level here, I have one value here, which is K. I have an equal and opposite value here, which is minus K. Okay, remember, we're only talking about valence band now. There are no electrons anywhere else. So I can pick any energy level. They're always symmetric, as long as this is parabolic. So it's under that assumption. Okay. So electron, this means electron moving in this direction, let's say. This means electron moving in that direction. Okay. Of course, they cancel each other out. There's no net charge transfer, so that's why the current is 0. Okay. Now, so in a filled valence band, there can be no current, as shown here. For every electron with the velocity v, there's another electron with an opposite velocity minus v. Now, when you have the situation, okay, I'll go through that. So that's calculate the current density. You just add up the velocities of the electrons. Electron velocity times the electronic charge. N is the electron density, which is units per centimeter cube. Okay, all that straightforward. Q is the electron charge, which for those of you who may not remember is 1.6 10⁻⁻19 coulombs. Okay, this is charge of an electron. Now, what happens if you remove one electron into the conduction band? Okay. Now, our sum now becomes, let's say we remove the jth electron. It's taken away from the valence band. This electron is gone. Okay. So we have to add that into the equation. So you have to add an extra term into that sum, which means that now you have a term which looks like that. So now your current is given by plus Q times velocity. So it's the opposite charge of an electron. So of course, if you think about it, it makes common sense. An absence of an electron should behave like a positively charged particle. Right? The electron's gone. Okay, that's what's called a hole. Okay, so the hole is equivalent to current carried. The whole current is equivalent to current carried by a particle of positive charge Q and the same velocity as the electron. So that's the model we need to use. Electron straightforward. So if you apply, so I have a practice question for you. If you apply an electric field which looks like that, okay, which way will the electron move? Yes, exactly. It will move opposite to the field. Right? It's obvious, right? Because if you feel like that has to be applied with a positive charge here and negative charge here, right? The electron has to move away. Which way will the hole move? Same direction, because it's positive charge. Okay? So keep that in mind. This is why it's important to consider them separately when we actually calculate currents in semiconductors. Okay, keep this in mind when you look at some of the review problems later on. Okay, we can also look at this in a cartoon. essentially shown here. So imagine that this electron has been kicked off from here into the conduction band. Of course, this is real space, so we cannot show different energies, but imagine it's kicked in, it has higher energy, okay, it's in the conduction band. So that's our hole. So the way the hole will move, of course, hole is an absence of an electron. So the way a hole can move is if some other electron in the valence band comes into it and fills it, right? So the picture, if I may draw, would be something like this, right? If I have, let's say I have a very regular array of everything filled with electrons except this box, okay? That's my hole. The way the hole can move is, let's say this electron jumps here, okay? Now, this becomes the hole. This becomes the electron, okay? And then this electron jumps here. This becomes it. So the hole can travel because the electron travels the other way. So that's the way to think about it as well. So hole conduction goes the opposite direction to the electron conduction. So what direction is the current flow? It's shown here. So current flows this way still. Current flow is opposite to the electron. Okay, all of this is very basic, but it's in the same direction of the hole. Which direction is the electric field in this case? It goes from plus to minus, right? Okay, so it's the same as what we just did. Keep this picture in mind. This is very important because you need to understand this conceptually before we start doing some simple math. Okay, and it's not necessarily very intuitive, so you need to think a little bit. Okay, so another way to look at these things is by looking at the band diagram. Okay, applying electric field and looking at currents, I mean. Okay, remember, we can look at band diagrams in two ways. We can draw the simplified band diagram, which is basically a straight line, and imagine a valence band and a conduction band. Or we can have these three-dimensional structures. Okay. Now, when you apply an electric field, the band diagrams get modified. Okay? And it's difficult to show this with a complicated three-dimensional structure, so we usually show it with a simple line, where the line represents the bottom of the conduction band or the top of the valence band. Okay, let's just look at an example. So in this case, so this now, for the simplified band diagram, this horizontal axis is now position, okay, not momentum. For this full structured band diagram, the horizontal axis is still momentum. This is just overlaid on top of the simple diagram, so don't get confused. They're not together. Okay. So when you apply an electric field, what happens is that the bands bend. Okay. So in this case, when electric field is applied, the conduction band and the valence band shows a slope. Okay. And clearly, electrons like to go from high energy to low energy. They're always trying to minimize energy, which means that, and this is electron energy going up, which means that the electron will flow down. Okay? And the electric field is applied in this direction. Sorry, in this direction. Okay? Now, we can also correlate this with the EK band diagrams, which is the more complicated structure. And essentially all that means is that the band diagram is shifted up in energy relative to each other. Okay, so you can see this band now moves up when electric field is applied. So, and that's a simplified band diagram. That's the electron energy increases that direction, and the hole energy increases in that direction. So keep that in mind as well. Okay. Well, this sort of a picture of current flow will become very important in the next coming weeks. So I want you to think about this carefully. When you have a band diagram which is distorted like this, the electrons will flow down the band, which is trying to minimize its energy, and the holes will flow up the band, because it is trying to minimize its energy as well. Okay? It's an important picture to keep in mind before we actually jump into the mathematics. So think about that also. All particles prefer to minimize their energy. So holes tend to be near the top of the valence band in general, and electrons tend to be near the bottom of the conduction band, which we know. But when you apply an electric field, they also tend to minimize energy. That's another way to think about current flow. Okay. Okay. So just to reiterate this point, if you look at that point there, the K is 0, momentum is 0, the electrons are at rest. The electron velocity and the kinetic energy is 0. This is only the potential energy. Okay? At the top of the valence band down here, it's not shown. At K equals 0 represents the 0 kinetic energy as well. K equals 0 means velocity is 0, so there's no kinetic energy. So it's always only the potential energy. Okay? Now, the simple band diagram is a plot of the lowest point of the conduction band or the highest point of the valence band as a function of space. Okay? In other words, the simple band diagram shows the potential energy that the electron sees as a function of location within a crystal. Okay? It's another way to think about it. Okay? Now, of course, the potential energy will change if you apply voltage, electric field. That's the definition of potential energy. The volt is an electric field, right? The slope of the band is now the applied electric field. Okay. The electron here has gained kinetic energy relative to the electron here from the electric field. Okay, so this electron up here is more energetic than the electron here, so it tries to come down. Okay. The electron, and the process of it coming down, as I said, is not just a simple flow down. Typically, it involves a couple of complicated processes which we can approximate as a simple flow down. But you should remember that it has to lose momentum as well. Because remember, it is going. So first, for instance, it can lose momentum and maintain the energy, or very close to the energy state, okay, and reach this point of this band diagram, so this energy level. And then it can lose energy down to this point. Okay. So remember, the challenge here is that you need to also change momentum. So you have two things happening. You have to lose energy as heat in the crystal lattice, which is resistance of a material. That's how it gets hot, for instance, when you pass a current through a semiconductor or any material, for instance. It's because the electrons will collide with the crystal lattice and release heat. Okay, it has to change momentum and energy. Okay, so the net result, as I said, is that the electron just moves down the band. The actual process itself can be more complicated than that. And that was just an example. It doesn't need to be that particular way. Okay. Now let's look at what happens when you have a free electron. Okay, and take some pictures from there. There's no potential energy. So it's only kinetic energy, and it's from a classical perspective, we know it's just a parabola. Looks like that. Okay. So the momentum of the electron is given by P equals mv is just h bar times k. Okay, we know that from quantum mechanics. Kinetic energy is given by half mv squared, or half p squared over m of h, or h bar squared over 2m times k squared. Okay. Now, if you look at this equation, that's just the band diagram, right? It's relating energy to momentum. Okay, that's what we have been drawing so far. Okay, and of course, h bar and 2m are constants; they don't change. So this is an equation of a parabola. Right? So y equals ax squared. This is the equation of a parabola. Okay. So that's why we say that the band structure near the bottom of the band, of the conduction band, or the top of the valence band can be approximated as a parabola. And the potential energy is very small. Here we assume potential energy is 0. Okay? So it's a parabola. Now, we are going to introduce a very important concept called effective mass. Okay? So now, from this equation, we can relate the electron mass to the curvature of the parabola as follows. The second derivative of the electron energy level energy as a function of the momentum, with respect to the momentum, is h bar over square over m. Okay, this just comes from that equation, right? It comes from here. You can take dy over dx 2ax squared by squared is 2a. Okay, so the constant times 2, constant of the parabola times 2 is just the second derivative. Okay, this turns out to be very important, so keep that in mind. We'll come back to that in a second. But you can see that the mass of the electron now depends on the energy. I told you earlier that the mass is a constant. It's not strictly true. Okay? It's a little bit counterintuitive, but if you think about this, in this case it's true if it's a pure parabola, constant. But if it's not a parabola, and most band diagrams are not always parabola, you can see that this m is now dependent on energy, okay? Which is not that counterintuitive. We'll look at this closely in a second. But think about that a second. Which way the electron is moving determines how massive it is. Okay? A little bit strange if you think about it. Okay? So the electron mass can change depending upon its energy and its direction of travel. Okay? Now let's look at that a bit more closely. This is this idea of effective mass. Okay? In order to visualize this, let's look at the wave function and how it behaves within a crystal lattice. Okay? So let's take a look at these two situations. So we have a wave function which looks like this, shown in blue, and the crystal lattice shown as these black dots. Okay? In this case, where they are shifted such that the wave function is mostly in between the black dots, it sees lower potential energy, right? As opposed to when there's a little more overlap of the wave function with the black dots. Remember, the black dots is the negative of the potential energy. Okay? Recall that the potential energy of an atom is kind of something like that, right? This is energy. This is position. So more of the wave function sits here means you have lower potential energy than if it sits outside. Okay? So in other words, this electron wave interacts with the lattice less strongly than this one does, which means that one would expect this electron to move a little more freely than this one does. Or another way to think about it is that this electron could be a little bit heavier than this electron. That's a qualitative way to think about what effective mass means. So the wave function can determine how heavy a particle is. Okay? We'll look at something more specific to drive home this point. So let's come back to the band diagram of gallium arsenide. Okay? As we saw before. So the first question is that at the band minima, as I said before, at the lowest part of the bands, the potential energy is minimized, which means that from the expression that we derived a couple of slides ago, those bands should look close to a parabola. Okay? So at the band minimum, most energy bands look like parabola, so we can approximate the mass as h bar squared divided by partial d squared e over dk squared. Okay? That's just from the last 2 slides ago. Okay? Now we write a star there to say that it's an effective mass. Okay, now let me ask the question. Which effective mass is larger? Now I want you to talk to your partner for 30 seconds and give me an answer. Okay, discuss. Okay, so first we need to remember that these two represent two different directions of the crystal. This is k equals 0, so it represents some particular direction of the crystal. And this is k not equal to 0, so it's another direction of the crystal. We're looking at two different directions of propagation of the electron in a crystal. So that's a physical picture to keep in mind. Okay? So to answer this question, of course, we need to look at this part, d squared E over dk squared of those curves, right? Because h bar squared is a constant. That doesn't change. That's Planck's constant. Reduced Planck's constant. So in other words, if you look here and look here, which one has the higher radius of curvature? Right? That's what that means, right? The second remember, first derivative is just the slope. Second derivative is the radius of curvature, just coming from differential geometry. So which one does? The one here. The curvature is larger here, right? Obviously. So the effective mass is smaller. Okay. In other words, the electron at the bottom of the conduction band is lighter than the electron further away. Again, very counterintuitive if you think about it. That's the way nature works. Okay? Another curious thing. The curvature is negative there. What does that mean? It means the effective mass is negative. You can have negative effective mass. Right? Of course, this means the energy is flipped. For a hole, the energy is flipped. That's what that means. Okay? The effective mass of an electron on top of the, so for a hole, now we're talking about electrons, so the hole it'll be different. So the effective mass of the electron at the top of the valence band can be negative. It is negative. Okay? Essentially, what all that means is that it is trapped. It's not free to move, basically. Okay? If you think about it, all it means is that its kinetic energy is negative. It's negative, basically. Okay? And this is why it's counterintuitive when we have to use the hole motion to explain. It's much easier to use the holes to explain charge carrier conduction, current conduction in semiconductors, using holes rather than with electrons. Okay. Okay, the effective mass can also vary with direction, as I said before. Okay, now let's look at silicon, the band diagram of silicon. It's a bit more complicated. First of all, you have lots of bands here. So let's look at the axis first. So you have conduction band up here, valence band down here, the wave vector here. So this is gamma, that's L, that's X. This direction is the 111 direction in the silicon crystal. This is the 100 direction in the silicon crystal. So we're only looking at two projections in the 3D space, okay? Two slices of 3D space. That's the picture I want you to keep in mind. Energy in two different directions. Okay. The first point we want to make is that the lowest part of the conduction band here is roughly parabolic. The highest part of the valence band here is roughly parabolic. Of course, in the indirect band gap semiconductor, silicon. But as you increase the energy, it's no longer very parabolic. Okay? Which means that it's much more complicated in terms of solving the equations and so on. You can't use the simple assumption. In the valence band, you see two valence bands which roughly have the same energy, and they have two different curvatures. You have what's called a heavy hole band, so it's a little bit heavier because you have a lower radius of curvature, and then you have a light hole band, which is a larger radius of curvature. Okay? So in gallium arsenide, the equivalent thing happens as well. Again, we have a conduction band, we have a valence band. In this case, of course, it's a direct band gap semiconductor, so the bottom of the valence band corresponds to the bottom of the conduction band corresponds to the top of the valence band. Now, the same sort of things can be said here. As you go up in energy, it's no longer parabolic. Okay? Remember, when it's not parabolic, that means that the mass is also changing with energy. That means this term here, E squared E over K squared, is a function of energy as well. It's not a constant. Of course, mass depends on that, so it's a function of mass. Mass is a function of energy as well. Its curvature changes with energy, essentially. Okay. The other things, of course, are that this is parabolic here, parabolic there, and you still see two bands here. Their curvature are pretty close, so they're about the same mass. Excuse me, for holes. Okay, so those are the important things. We'll come back to that. So in order to visualize the effective mass, there's another way to look at it. It's based on what's called the constant energy surface. Okay, and this is drawn here for silicon. This is drawn here for silicon at the conduction band minimum. So remember, at the bottom of the conduction band in the band diagram. The way you draw this is basically for a given value of energy, you find all the k vectors that can give rise to this electron energy. So you look at the band structure, you pick some energy, find all the k vectors that can correspond to that energy, then you draw a locus, a surface. Okay? This is kx, ky, kz, and then a surface of constant energy. So anywhere on the surface, the electron has the same energy. Okay? So constant energy surface in k space. Now, if you look at this, you can see it's not a sphere. Which means, remember, the curvature of this surface is the mass. It's related to the mass. This is still, remember, even in a constant energy surface, that's still valid. Okay, this is inversely proportional to the mass. So you can see, but it's an ellipsoid in silicon. You can see there's a longitudinal mass, which is much higher than a transverse mass of the electron. So although the electron might have the same energy, anywhere on the surface, it will have different mass. Okay? Now, for all intents and purposes, when we actually do the current calculations, we will average the mass over all the directions of interest. Because typically, it's not the electron doesn't just travel along a single direction, it travels along a range of directions. It also has a range of energies. So you have to average over directions, and you have to average over energies when we actually do the calculations. But I want you to keep this picture in mind that the mass depends on direction, very close to the bottom of the bands, or the top of the valence band for the whole. And it can depend on energy as well. And it's far away from the band maximum or minimum. Okay? It takes a little bit of thinking to getting used to it. So it's okay if you're a little confused with it. My suggestion would be go back and think about this. Okay? And try to read the text a little bit. So you have a longitudinal effective mass, and you have a transverse effective mass. Okay, so again, just to drive home the point, the effective mass is nothing but a mathematical concept. There's nothing strange about it. Mass of electron, the actual mass of an electron is still whatever it is. It's not changing. The effective mass is just a mathematical concept that explains the motion of the electron in a crystal. So keep that in mind. Okay? It just enables us to simplify the math. It enables us to incorporate the crystal potential without actually calculating it carefully. You can incorporate that into all the mechanical equations. Yes?
It's also like representation of the inertia needed to move it?
Yes. That's a way to think about it. So you have a potential which is preventing the electron from moving. So it's an inertia from it not being able to move. The real mass of the electron is the same in any crystal, the actual mass. Okay? And one can always relate the actual mass to the effective mass, as we will see later on. So, okay, now we want to use the rest of the time to talk about two kinds of semiconductors which turn out to be very important, and it will be much more relevant for next week. But we need to understand what they mean. There's something called intrinsic and extrinsic. The ideas are very simple. Intrinsic semiconductors are ones which have no impurities. They're completely pure. So pure silicon, pure germanium, pure gallium arsenide, whatever. No defects. Of course, that's not real. All crystals have defects, but this is a theoretical construct. Okay? Intrinsic semiconductor means this is what we have been seeing so far. The valence band is completely full. The conduction band is completely empty. They're separated by band gap. Okay? At 0 Kelvin, no free carriers. It's an insulator. At room temperature or at a temperature higher than 0 Kelvin, electrons are excited from the valence band into the conduction band. You have holes here, you have electrons here. These electron-hole pairs are the only charge carriers in an intrinsic semiconductor. Okay, nothing else. So it's easy to analyze them. Remember, also, one electron gives rise to one hole. So the number of electrons is equal to the number of holes in an intrinsic semiconductor. Again, much easier to analyze. Okay. The quantitative picture of electron-hole pair generation is fairly straightforward. All it means is that, let's say, we have a bond here that has been broken, which means that the electron has been kicked out. It has been kicked out from the valence band into the conduction band, or in other words, it has gained enough thermal energy to break the bond and go away and travel. Okay? At T equals 0 Kelvin, a covalent bond may be broken. So remember, this is silicon. So silicon shares one electron with its neighbor, 4 neighbors. So 4 electrons shared with 4 neighbors. Each bond has 2 electrons. Remember? That's the picture of silicon, which we saw last class. I think. Okay? So now it has a hole. Okay? The electron's free to move, say it's somewhere here, and it has a hole. So that's an electron-hole pair. Okay? But typically, it's not localized like this. It is spread out. I mean, a hole just doesn't stay put because of the thermal energy. It's always hopping around, as is the electron. Okay? The electron, of course, now is free to move about the lattice in the conduction band because it has extra energy. Of course, we don't see energy in this sort of a picture. This is real space. But remember, the electron has extra energy, so it's moving around. And the hole is free to move about in the lattice in the valence band. Okay? Just like we saw before. The energy required to break the bond, in this case, is the band gap. Eg. Has to, at least the band gap. You have more than that. So this is the real space picture of electron-hole pair generation in an intrinsic semiconductor. No impurities, no defects. Okay, so since there's for each electron, like I said, there's one hole, we can write very simply that the concentration of electrons is equal to the concentration of holes is equal to an intrinsic concentration, Ni. Okay? It just doesn't change, right? Now, of course, what will this depend on? What will this concentration depend on? Any thoughts? The mass of the electron? Yes, it can depend on the mass. Anything else? Most importantly, how are they generated?
How much pressure?
Yes, by the heat, right? So it depends on temperature. It's most sensitive to temperature. Higher the temperature, the more of them generated. So we would expect them to increase with temperature. Okay? We will talk about that quantitatively in the next class, I think, but keep that in mind. Oops. So at steady state, no energy input, no energy output. Okay, that's what's referred to as steady state, equilibrium. This thermal generation of electron-hole pairs must be balanced by an opposite process called recombination of electron-hole pairs. Otherwise, it's not steady state, right? Imagine this was the only thing that's happening. Oops. Imagine this is the only thing that's happening. And after a while, all the electrons will end up in the conduction band, right? Of course, that cannot happen because that means you are just putting in energy. But imagine a semiconductor which is in thermal equilibrium with the surroundings. So it's not gaining any energy, it's not losing any energy. Any electron which is excited up to the valence band must also come down to the valence band at some rate. So you have a steady state distribution. So you have a steady state concentration of electrons here, steady state concentration of holes here. Okay? That's what we're talking about. Okay, so what that means is that the energy going in to create the electron hole pair generation must be matched by the energy going out of the system, which is by recombination, where the electron hole pairs combine together and release energy, which can be heat, light, whatever. Okay? So the generation process and the recombination process have to be matched. We will come back to this in a bit more detail in the next few weeks, but right now what you need to remember is that this recombination rate, the rate at which electron hole pairs cease to exist, is equal to the rate at which the generation rate, the rate at which electron hole pairs are created, which of course makes sense because it's an equilibrium, which means that this concentration does not change with time. Yes?
So when you say at steady state, are you referring to not giving off or receiving energy?
Yes.
Okay.
Exactly. So that's what's happening. If you think about this, energy is coming in, energy is going out. There's always exchange of energy. It's not a completely isolated system, but they're equal. Okay, the thermal equilibrium with the surroundings. This is a very important condition, which you probably have seen in your introductory thermodynamics, and we'll come back to this again and again. The equilibrium condition. Okay, the semiconductor is, okay, good. The semiconductor is not gaining, is at a steady temperature with its surroundings. That's basically what that means. It's not gaining heat or losing heat. Okay? Okay, in that situation, these rates, of course, also depend upon temperature. As I said before, the carrier concentrations, of course, depend on temperatures. So at a higher temperature, so if you heat up your surroundings or heat up the silicon crystal, it will reach a new equilibrium. That's all that means. Given enough time, of course. Needs time to reach the equilibrium. Okay? And we can model the rates as proportional to the concentrations of the carriers by some constant. So the recombination rate as well as the generation rate is some constant alpha times n naught times p naught, which makes sense, right? If you think about it, the probability of an electron hole pair generation, we'll come back to this. If you think about it, probability of an electron hole pair generation depends on how many electrons are actually there in the valence band first, right? If there are more electrons in the valence band, there's a higher probability some of them will get excited. So it has to depend on the carriers that are already present. Okay? That is this side, Ni squared. Okay? The generation, of course, if there are electron hole pairs around, the recombination, of course, depends on whether there are electron hole pairs around. The more there are, the higher the probability that they will recombine. Okay? Which is this part. Electron concentration times the hole concentration. Just as a convention, we refer to the electron concentration as N because the negative charge, and P for the hole concentration because of the positive charge. Keep that in mind, but we'll see this again and again. Okay, now the last topic I want to cover today is the other part, extrinsic semiconductors. What does that mean? Okay, intrinsic semiconductors are pure semiconductors, no defects, nothing in them. Okay? Extrinsic semiconductors have impurities in the crystal, either defects or actual material impurities, okay? To create more electrons or holes so they're more conductive, basically. So we have two types. You have an N type, where you create mostly electrons, or you have P type, where you create mostly holes. Keep that in mind. How does this work? The most common example is silicon that is doped with a donor impurity. Donor means that impurity is an atom that gives away an electron. It donates an electron to silicon. Okay? And this could be phosphorus, arsenic, antimony. Any atom which has 5 electrons in the outer shell. So if you have 5 electrons like phosphorus, 4 of them can, of course, bond with the neighboring 4 silicon atoms. But the last 5th electron is free. It's weakly bound to the phosphorus nucleus, which means it can float around very easily. Okay? That's the real space picture. In an energy space picture, the way to think about this, that the impurity introduces an extra energy level within the band gap. Remember, the band gap represents the forbidden energy level. There are no energy levels there, so nothing can exist there. But when you add an impurity, you add an energy level there, okay, as shown by ED. This level is filled with electrons at 0 Kelvin. And that picture, that filling of those that energy level with electrons is the same picture as the fifth electron of phosphorus not being tightly bound to the nucleus. So it's in that level. Okay? It can be very easily excited up to the conduction band. That's the picture. That's a physical picture. Okay? So at a very small temperature, greater than 0 Kelvin, these electrons are very easily excited to the conduction band. Okay, this is also called the donor level because they are donating the electrons. The donor impurity donates electrons to the lattice. So now you see something strange, right? There are no holes here. There are plenty of electrons here, no holes. There are many more electrons than holes. That's why it's called an N-type semiconductor. So our old analysis of the intrinsic semiconductor where the concentration of holes is equal to the concentration of electrons is not valid anymore. Keep that in mind. It's an important difference. Okay? The other important difference is that clearly this energy difference is very small, which means that you can excite these electrons up much easily than in an intrinsic semiconductor. The other important point to keep in mind is that now you can control the concentration of electrons irrespective of temperature. Because the concentration is now controlled by how many dopant impurities are in there, which is what you do when you make the silicon. You can add more, you can add less. No longer just temperature dependent. As an engineer, I can control it. Very important. Technologically, very, very important. The reason that we have transistors and so on. Okay. Now, of course, we have the p-type. For p-type, you have what I call acceptor impurities. In silicon, they are boron, aluminum, gallium, indium, and so on. These are elements with 3 electrons in the outer shell. Okay. So what happens with the 3 electrons? Of course, they bond with the 3 neighboring silicon atoms, and you have 1 extra bond with another 4th neighboring silicon atom which is not fully filled. Okay? That not fully filled bond has a hole, basically. There's no electron there. That's the physical picture again. Okay? In the energy diagram, it's again very simple. The acceptor introduces an energy level in the band gap close to the valence band, the bottom here, and it's empty at 0 Kelvin. Okay? But of course, it's very close to the valence band, which means that at a small temperature, the electrons can be excited very easily to this level, this acceptor level. Acceptor because it accepts the electrons. In the physical picture, what does that mean? You have an empty level in a covalent bond, which can then accept an electron and fill that level and create a hole somewhere else. Okay? That's the physical picture. Now, of course, here, this can happen again. Just like the donor, you can control this irrespective of temperature by controlling the concentration of acceptor atoms that you add. It's a big technological advantage. Again, if you look at this picture, there are no electrons in the conduction band. There are plenty of holes. So it's a p-type semiconductor. Okay? An analogous picture as well. Okay. So this is just to reiterate the point. In this case, the donor arsenic has 5 electrons, 4 of them form covalent bonds with 4 neighboring silicon atoms. The last electron is weakly bound to the arsenic nucleus and can be easily donated to the crystal for conduction to the lattice. So that's the arsenic. You have an extra electron that's very easily excited into the conduction band. For a donor, the opposite happens. The boron has 3 electrons, which means all of them form these 3 bonds with the neighboring silicon atoms, but the 4th neighbor is an incomplete bond. So it's a hole, which can very easily move around in the valence band. Okay, and that's a physical picture. Okay? I need you to understand both of them because the energy band structure is an abstraction. You need to really understand also the physical picture to make sense of all of this. The importance of doping can be understood by putting some numbers in. Okay? In silicon, the intrinsic carrier concentration, as we saw before, at room temperature is about 10 raised to 10 per centimeter cube. That's just whatever. It's determined, of course, with the band gap, right? Larger the band gap, this number is smaller. Smaller the band gap, this number is larger. We'll see that again. If we add arsenic atoms at a concentration of 10 raised to 15 per centimeter cube, which, by the way, is a small concentration. Why? Because the silicon atomic density was something like 10 raised to 23, right? Now we are talking about adding in impurities which are 6 orders of magnitude lower concentration. That's a pretty small amount of impurity. But if you see that, this small amount of impurity can swamp these intrinsic carrier concentration by 5 orders of magnitude. In other words, the doping can make a huge difference in the conductivity of silicon, a little bit of doping. That's what it tells me. Okay? So another terminology you should be aware of, in this N-type silicon, the electrons are majority carriers, which is obvious because there are more electrons. The small number of holes are also present. So my picture earlier where there were no holes is not exactly true because there's always some holes because of the thermal excitation. But they're very small, and they're referred to as the minority carriers. When we calculate current next week, we will have to account for both the majority carriers and the minority carriers. So keep this picture in mind. Of course, the situation is vice versa in P-type, where you have the holes as the majority carriers and the electrons as the minority carriers. Okay? Okay, I'll stop here. Then we'll finish this part up next Tuesday. Okay. Oh, the review session. Sorry, I meant to. So for the review session on Friday, the TA is going to go over some of the previous problems. I know if you have problems, and I know he didn't finish all of it. And there were 2 more problems from chapter 3. Okay. This is 3.1 and 3.10. Okay? So if you don't come to the review session, try to do them yourself.
Is he going to still do the problem that you did on Monday?
Yes, if you want to. So you can ask him and he can do that.
Oh, okay.
I think he wasn't able to finish it, so he will probably read it to us. But you can just ask him. He can go through it. But try to do it yourself too before you come.